So, shall we start? Are you ready, Julian?
Oh, sure.
Sure. Okay. Um, yes. Hi. Nice to meet you all. And actually, today is our workshop, the UVAM in multimedia. And we are glad to invite two great speakers, the Julian and the Javen. And Javen will come later. And first, we will welcome our Julian. He is the professor. He is the associate professor at the TU Delft, and he works on the slam and many interesting things. And yes, let's welcome Julia. Yeah. Uh,
Let me share my slides again. Thank you very much for this invitation. I hope you can hear me well and you can see me. And yeah, presenting from a different time zone. Sorry, I couldn't join. I'm presenting from the Netherlands, where I'm indeed associate professor at TU Delft in the Intelligent Vehicles group. I'll give some short overview of myself first. So currently I'm associate professor. I actually did my PhD at the University of Amsterdam in the Netherlands. During that time, I also spent some time at Daimler in Germany. So Daimler is the company behind Mercedes. So back then, research was based on vision from the vehicle and predicting road user behavior. So here for cyclists, this was in the pre-deep learning time. Um, is my presentation visible?
yes, yes, I
Yeah.
will just full screen your slides. Yeah, thanks.
Yeah. Um, and right now at Delft University, we're also still doing a lot of research with our vehicle. We have a team covering all kinds of different topics within the technology within a vehicle. We also do these kind of demos. Here was at RSS, robotics conference, in the test track behind our lab, where you can see that with our vehicle we can do yeah, real closed loop testing with dummies, for example. And you saw the no hands on the wheel example. We're really driving here autonomously and closing the whole loop. My own research is focused on perception. You see in this video, I'm not sure if the audio is hearable. We do, for example, experiments with microphones. So we can detect in this video, you see, with microphones mounted on the vehicle, we can detect road users approaching by hearing where they are coming from. And we also can do data collection in the center of Delft, for example, with 4D radar. So that's radar that also has elevation. So I'm basically interested in a lot of different topics related to perception using different sensing modalities and being able to predict what will happen in the future. Some other lab that I'm involved in is the 3D Urban Understanding Lab that I started together with the professor Liang Nan from the architecture faculty. Here we combine different topics, looking both from aerial imagery as well as from the road level imagery with our vehicle, and combining this type of research topics for both topics like localization, reconstruction, but also object detection and semantic segmentation. So this is a bit of an overview of the research and of our group at the Intelligent Vehicles Group at TU Delft. And we also have a website, intelligentvehicles.org. So if you want to learn more about us, then I would say maybe you can visit us there. And now I want to focus a bit more on the topic of this talk and about the topic of localization, specifically about why, maybe first, what's the problem, right? Why is GPS or GNSS not really solving all our localizations problems, especially from self-driving vehicles? So here's a plot, a track from the Oxford Robocar dataset, and they actually have a lot of runs. It's a quite famous dataset in our field. And what you can see in green is the ground truth trajectory, the road that have been driving for many days. So they have a very accurate route of that. But you can also see in red these raw GPS measurements. And you can see that at some places it works very well, but at other places there are these huge jumps. And if you plot over time the error in meters between the true location and what the GPS reports, you can see that sometimes it jumps up to 50 or even 70 meters. So the raw GPS signal itself is not very accurate, and we can do all kinds of things of smoothing, but there will be delays, and sometimes there's like whole periods where the GPS is inaccurate. So in practice for self-driving, we have alternative strategies such as, of course, SLAM, and here on the left is a classic SLAM method that we ran many years ago when we were trying to do with our stereo camera. So you see this stitching of the point clouds. You get these really highly detailed maps of the environment. You can optimize these, but they represent every little detail in the map. So every leaf, and as soon as the leaves fall from the trees, then this map might not be accurate anymore. So this is sort of the common approach. And if you have one specific route, you would really map this out, maybe with your LiDAR, maybe with your camera, some combination. But then there's a lot of effort in keeping these maps up to date, and it doesn't really scale if you want to cover and expose your self-driving system to many parts of the world. So one of the questions that we had is, can we maybe do localization in a different approach where we get the maps for cheap? And why not use some aerial imagery, something that you could get from Google Earth, but Google actually they collect their data also from other providers. You can buy this. In some countries, governments actually provide this kind of data for free. We have this aerial imagery. And would it not be nice if we could use those maps and use that to localize our vehicle? Because you can just fly with a plane over a city and then quickly map it out. And then hopefully you can take the images from your car and match that to this aerial imagery. So here's an example of a image from also London. You see there's some road work happening here. And we have this aerial view of the rough location, the rough neighborhood of where this car should be located. Of course, we can still use the GPS to get this rough idea. And our idea is that we want to be able to match this image to these different locations. We're basically turning this into a matching problem. So does what we see here match the content of what we would expect to see if we were at this location? Not sure. Can you see my mouse actually? Maybe I should turn it into a pointer. One moment. Yes. Does it match what we would expect to see if we were located here, there, or there? And if we could create sort of a distribution of these matches, so what you see here in red, we could estimate the location, and possibly we could even estimate the orientation, the full pose of the vehicle. And in this figure, you see that the true location here was in green with green arrow pointing in that direction, and our estimated location would be on top of it, pointing in the same direction. So yeah, ideally, if we do a good job, our star here, our predicted location, would be on top of the ground truth pose. And of course, this star is basically the peak of our distribution, of our predicted distribution that you see here in red. So this is the goal of what we call cross-view localization. And we have some works on that. I would like to first introduce this work that we presented at CVPR in 2023, geometry guided aggregation for cross-view pose estimation, and the method's called slice match. And by the way, this work was done by Ted Lens, who's now a PhD in our group, and Simon Xia, who will be presenting his PhD thesis very soon, also together with my colleague Holger. So first, yeah, the method is called slice match. So what is a slice? Well, here we have a panoramic view of the environment from our vehicle. You could think of a Google Street View image over here. And let's say that we would know the true location of where this uh, panoramic camera image was taken. And it could be this green location over here with the little stick that you see here indicating the forward direction of the vehicle. Then we could think of the different viewing directions in this panoramic images as slices that we see here in the panoramic images. They should correspond to the slices that I see here in the aerial view. If we number them, so in front of us of the vehicle, this is what's at slice 4 and 5, and this is indeed the forward direction over here. And you could see slice 1 and 8 are behind us, because this is a panoramic view turning all around us. So the visual content that we are seeing in these slices from the panoramic images should match the visual content up to some extent of what we're seeing here in the aerial view, right? So if I'm looking here along the road and I'm seeing a building over there in slice 7, then I should see at a similar distance also the building over there in slice 7 and the road in slices 4 and 5, and maybe somewhat in 1 and 8 as well. So our goal is to extract some features that represent the visual content of these individual slices in the camera images. And if we could have similar features from these aerial image from the multiple slices, then we could construct these into one big feature factor. And if this is the correct location, we could think of these feature factors as that they should match. We could have some sort of cosine similarity matching score saying that these two vectors should be close together in this big feature space. Now we could test that not for this one pose, but maybe for many poses. So here in purple, you see all kinds of hypotheses because of course, in reality, we don't know what the true location orientation is. This is the thing that we would like to find out. So if we could test it for a lot of different poses, and then for each of those poses, multiple viewing directions, then we could construct these kind of vectors for all of those poses and viewing directions. And we could match these to what we're seeing in the ground image and determine which of these poses is the best matching pose, and therefore indicating our camera. And we want to do this in an efficient way that minimizes the amount of computation. This is a big difference from the methods that were proposed before, including some of our own methods. So our idea is that we can become accurate if we can test a lot of these different poses and do that in an as efficient as possible way. Because the more efficient we can do this, the more poses we can test. So here the idea came of the slice masks, and they're in this aerial view. The slice masks, they say like, if we know what kind of poses we are interested in, we can pre-compute these regions in our aerial view that would correspond with the field of view that we would expect to see for this particular slice at a particular pose. So here, if this would be one of the poses that we would like to test with a particular forward direction, we can already pre-compute what would be these slices, what would be the spatial extent of each of these slices in the aerial view. And we could do that for all of these poses that we're interested in. And you can think of that these are simply binary masks, zeros and ones, that say 1 if you are inside the slice and 0 if you're outside of the slice. So for this pose, we would pre-compute 8 of those binary masks. We just store them in memory. And if we can do that and we can compute those poses, we can actually apply a simple contrastive learning strategy where we take the features from our panoramic ground level image and we would construct using these masks, and I'll show how to do that in a moment. We could construct also these big vectors representing all these different poses from the aerial view, and then we can do simple contrastive learning to train our model and make sure that the true ground level image matches the true pose and does not match the visual content of the wrong poses. So how do we achieve that more concretely? Well, we start, of course, with our input. So the input is the aerial image over here, where we have a rough idea based on our GPS prior where we should be. And we have our ground level image, and we have a whole set of different poses, locations, and orientations within this aerial view that we would want to test. And first, we extract features from both of these images using some backbone. Could be a CNN, could be something else, doesn't really matter, as long as we obtain some feature map from these images. And then first we take a look at the backbone features from the ground image. We apply some self-intention mechanism, pretty standard. And then we get this feature map where all of these different cells and different features, they correspond to different regions in this ground level image, and we divide that in our n different slices, in our different viewing directions. For each of those slices, we pull the features inside our feature map, and this way we get our n descriptors of each of these slices. And as we saw before, if we would simply concatenate that, that would create one big descriptor of this whole ground level image. Now we take a look at the feature map that we get from the ground level image, and we're going to look where we can identify the same information that we see in each of these ground slices. So we have n of these ground level slices for each of these descriptors for each of the different viewing directions. We're going to match it to the information that we extracted with our backbone in our aerial view. So this is a cross view attention. And you basically get these attention maps for each of the n viewing directions in our ground image that tell us how much of this information is matching what we're seeing in the in the aerial image. So we have these n attention maps. Now we take our poses, and for each of these poses, we have our pre-computed slice mask. So we could take one of these poses, for example, the one here located and looking in that direction. We take the slice mask, and now the operation is pretty simple. We combine the slice mask with these feature maps that we computed for each of the slices, and we simply aggregate all the information corresponding to that particular slice mask. And that's just a multiplication and a summation. So it's basically one big matrix multiplication of, if you consider this one big matrix and this matrix, you simply multiply them and sum them. And that results in again, a vector that describes the information for this particular slice of this particular pose extracted from this aerial view. And we do that for all the different slices that we have here in the aerial view. We get all these vectors, we concatenate that, and now we have the descriptor for this particular pose in the aerial view. If you do that for all the poses, you get basically a whole bunch of descriptors for all the different positions and orientations. And we can again simply apply our cosine similarity and obtain this heat map for all the tested poses, including their orientations, and select the pose that matches best. So this is the overview of this architecture. And why is this now so computationally efficient? So what's interesting to see is the feature extraction is only done once, and we minimize the number of operations for each of our pose hypotheses. And this is what's happening over here. The backbone, we run this once here, we run the backbone once here. This is all one forward pass. But now the more poses I have over here, I only need more pre-computed masks, and the cost that I pay for adding more poses is just some multiplications and summations, which is of course very cheap to do on the GPU. In the end, I need to do a cosine similarity, which is also cheap. But I don't need to run very expensive backbones or other feature extraction methods. So this is why this is so efficient, especially on the GPU. It's also very parallelizable. And okay, we tested this not on some small embedded system, but it's still a beefy GPU, but we reached orders of magnitude faster inference speeds than previous state of the art. So here we reached in our experiments like 150 frames per second. And if you try more poses, and we did some experiments also on how many slices to use, yeah, the frames per second was actually pretty constant. The only thing is that the more poses you add to test, the more pre-computed slice masks you need, and you pay in storage space. Though I think you can also still do some optimizations on that end. So we compared slice match to some of the baselines that were at that moment state of the art. Here you see we used some VGG16 backbones, not the strongest backbone, it was the backbone that was being used by the baseline. So we stuck to that to be able to compare with them. Clearly, if you use a better backbone, you can also get better results. And what you can see here is the location error in mean and median error, but also we have the orientation error. And we were really pushing down at that time the error in meters, both mean and median. So this is a bit more robust against outliers. down to, at this moment, 5 meters on some data sets. This is in the same area. This means we are testing here in the same area as that we trained, but with new ground level images. But we've seen the satellite imagery also during training. In cross areas that you go to a new location where you have never seen the satellite images. So this is a more difficult setting. And as you can expect, the errors are a bit higher here. Um, so actually one of the baselines here, the MCC method, was one of our earlier methods that we presented at ECCV in the year before in 2022. We've extended that work to a PAMI paper, which is actually now, I would say, the reference for that direction of work. It's also done by Simon together with Olaf Boy, who was from TomTom. So this was a nice collaboration. And I would say this is the more accurate method now that we have. So the same idea, we have a ground level image and we would like to locate it in some rough estimate of our local aerial surroundings. So we get this image from Google Maps. Of course, it's not the exact same location. It's not the exact same moment. So you see all these cars here. But this is just the cars that were taken when the aerial imagery was collected, but it's not necessarily the same objects that you see here in your ground level image. So first thing is that, again, we're going to treat this as a problem of trying to match the ground image to different locations in this aerial images. And you could think of that as sort of a multi-class classification problem, where we want to predict this distribution over possible location. And we want to do that very densely. And some of the previous work that I'm not discussing here, they treated it as a regression problem where you only regress one position. One of the novel ideas here was doing this multimodal distribution that also allows to capture ambiguity. So for example, we're seeing here that this ground level image is taken on top of, so the image from our vehicle is taken while the vehicle is crossing a zebra crossing. So you would expect that there are stronger responses for locations at zebra crossings over here, and lower responses outside of these zebra crossings. So you can think of this as a distribution of where am I located given my ground and aerial image. Now, the thing that we added here is also the idea to not only have the position, but also have the orientation estimation. So we did not have that in our original ECCV 2022 paper. And the way we solve here orientation is that we also estimate, as a function of our input images, a orientation field, a flow field here. So for each pixel, we're estimating an orientation, a direction. And you can interpret that as, if I would be located at that location, what would probably be my forward pointing direction? And you can see, for example, that this field has particular orientations, and the orientations change depending on where of this zebra crossings you would be, on which of these zebra crossings you would be located. So if I would be on this zebra crossing, and I know from my ground level image that I'm looking along the street, I'm probably looking in that direction. But if I would be at this zebra crossing over there, then I would be more looking into that direction. And if I would be maybe on the zebra crossing here in the top, I would be more looking for us to the south, down. So we're coupling here the orientation together with the position. For this, we have also a high-level view of how this would work. So again, we have our aerial image over here, and we would do some feature extraction, create some feature maps with X and Y location. So this would be east, west, and north-south direction. But we also again have multiple features. So this is the feature dimension, and you could think of different subsets of this feature space corresponding with information in different viewing directions that I would expect to see if I would be at that particular location in the aerial view. Similarly, in the ground branch, we do something similar that we saw in slice match. We slice it up, and we also again create descriptors for these different viewing directions. And now the idea is that we can actually compare these slices from these descriptors from our ground image to the descriptors of our aerial image, and we can do some cosine similarity and get some score, but we could also move the ground image or the aerial image relatively to each other in this feature space. So we're doing basically a convolution in the feature space, every time shifting a little bit the features and what we first call the forward direction, while it might first be matched to the south direction. As we shift it, we are also trying to match how well does the forward direction maybe match to the west or to the north or to the east, right? And for each of those different orientations, we get a matching score. So you can see here, if my forward direction was 0 degrees, so pointing north, or what if it was more pointing to the northeast or east or southeast or south? How well does it score? And we're doing that, of course, for all the points in our aerial feature map. So basically, for each of these directions, each of these viewing directions, you get a different matching score corresponding to how likely is it that I'm at this location if I am viewing and looking into a particular direction relative to my aerial view. So for each of those different viewing directions, we're getting these heat maps. And by collecting those heat maps and figuring out and asking ourselves if we put them all together, how likely is it that I'm at any of those locations? Well, then we get our final dense heat map that you see over here, huh? The red regions in which we could collect the most probable overall location. And we can also take all of these maps together and throw them through a decoder that will predict for us a flow field. And now we have both a location estimate, and we can look up for each of those locations that we find probable, what is the corresponding orientation that we would expect for that location. And the architecture is again pretty well, it starts pretty simple. There are a few different connections in here. But the starting point is that you have some backbone from the ground level image. As we saw before, we pull those ground level images for the different slices into different descriptors. So these are for the different viewing directions. We also have a backbone that we apply on our aerial images, and we divide that into a grid-like structure, and by N. And then we compare all of our ground level images to our um, aerial descriptors, but we do that comparison in two separate decoders. One decoder that is doing that to predict this heat map, and another decoder that's doing the same, a very similar operation, but then in the end predicting our flow field. And we have some modules in here that we call LMU and OMU. I will show them in a moment. But the basic idea is that this is done now in a coarse to fine strategy. So we start first with the lowest level where we have very rough idea of where the ground level image, the ground level features match the aerial information. And as we get a better matching score, we can zoom in a bit more, take more fine-grained features from the higher resolution, integrate those, and make our prediction every time a bit more fine-grained until we get this very high resolution matching scores. And we do that both in our localization decoder and the orientation decoder. And what's the difference between the two? Well, they both incorporate this concept of the rolling and matching, where we're trying to create these heat maps that tell us how well does the aerial image, the aerial feature map, match what we're seeing in a ground level image. So this rolling and matching, this convolution basically for the different orientations. But when we do the localization, we have this module where we actually in the end collect all these operations together because we don't really care about the orientation. We just want to know how well does the descriptor match any of those locations. So we max pool over all possible um, orientations, and then we get this one heat map that we concatenate to the features before, and then we do deconvolution to upscale the result into a finer grained step. This is one module that we're using multiple times, every time creating a more fine-grained matching result, and then upsampling that together with the features from our encoder. And when we do the orientation estimation, we have very similar operation, but we don't have the max pooling because we want to keep all the feature maps from, so these are all these heat maps for all the different orientations. We want to keep all that information separate when we do the upscaling, such that we don't lose our information of our orientation. So basically the localization becomes invariant to the orientation because it should still be the same location irrespective of what orientation we're looking at, while the orientation module does keep this orientation information. So this is a high-level picture of the architecture, but we can do some experiments, look at some results. So here you see 4 examples of a panoramic image together with some aerial view. You can see the arrows are the orientations that are being predicted, and the red again are the matching locations, so the heat maps. And we can see here again this example where we are located near a zebra crossing that we also see here in the ground level image, and that the orientations are, yeah, being mirrored around the center of this crossing. So for each different zebra crossing, it would correspond that if you would be located over there, that our viewing direction would be along that zebra crossing more or less. But only a few locations are actually matching very well with the visual content. So we only get those areas in red, and then we pick our most probable location and the corresponding arrow. And this is our prediction here in yellow, which really matches the green ground truth position and orientation. If you would have done the regression approach of previous baselines, it would always be somewhere in the middle, in between the different modes. So you can see, we have really in our method the ability to have some ambiguity. So in some cases we are not 100% sure. We pick some good location. Here's an example where we are in a park close in front of an entrance between some green spots. You see that all these green entrances have some high matching probability, but the correct location close to the green arrow is also the most probable match in our case. Here we have a failure case where we are predicting in the wrong pose in the wrong direction, with this street where there's very little visual information, but at least we know we're somewhere here across the street. We can also do experiments and see what happens, and I hope this video comes across well via the Zoom. But what happens if we virtually rotate the camera, which is very easy to do with panoramic images. And you can see that all the orientations move along as expected as we rotate this feature map, but the locations, so the red heat maps, are more or less the same. There's a little bit of a non-discrete, some sort of effect wiggling happening. That's because we have some slices again that are in discrete steps. So as we move around, there are some moments where the visual information is divided between different slices a little bit differently. This is why the whole map jitters a little bit, but especially within the red areas, the arrows really follow the orientation. But we can also apply our architecture. So this is very nice. We trained it with this panoramic view, but we can also test it when we don't have panoramic images at test time. So here we only have a smaller field of view, and clearly there's more ambiguity, more uncertainty. So you see that the red area is bigger, but you also see that the red area now changes depending on the visual information inside our camera view, right? Because in this left case, we always have the access to the full same visual information. It's just different direction that we're watching it. But here the visual information changes. So all these single frame results might be more or less ambiguity in that information. That's what you're seeing reflected here. And we also do experiments in our PAMI journal paper on how to train it. So if you train with both full panoramic 360-degree and also smaller field of view images, and you combine those together in your trainings time, you get actually really good performance at test time with all kinds of different field of views. So it's really beneficial to expose the network during training at diverse sets of field of use. Some other cool properties of this model is that because we have combined orientation and position information, we can also use any kind of prior information that we have about the orientation to filter out wrong poses. So if we have some ambiguities, here again, our zebra crossing example, in this case, here on the left, we assume we don't know the orientation. So we get this ground level image and we have this aerial view. And we again see that there are multiple locations that might be matching around the zebra crossing, because the zebra crossing could be this crossing, that crossing, that crossing, or that crossing. So we match in red a few different positions, and our most likely position by our network by a small margin is this position. So in the end, we pick this location and then the corresponding orientation. But as you can see, it's wrong because the true position orientation is over here in the bottom. But if I would know from some other sensor, maybe from time, or maybe I have just a compass, that I'm looking in the north direction, then I can include that information and filter out all these wrong locations. So I only have the locations that are also pointing up to the north. And now the ambiguity is solved and I know that I'm over here. So by coupling the orientation and the location, we can use any kind of prior information that we have about the orientation to improve our localization estimates. And of course, vice versa, it would work as well. If I know much better, more certain I am that I'm a particular pose, maybe also from some temporal filter, the better I can, the more certain I can be about the orientation. Here on the right is another example of the same type of situation with a lot of ambiguity and different orientations being associated with different possible locations. And if I know in what direction I'm looking up to a particular range, so it can be some uncertainty included, but the more certain I am, the better I can disambiguate the pose just using the known orientation. So if we look at the CCVPE, it's actually outperformed slice match. So the previous paper that I presented and also some other baselines at the time. And we are here, we pushed it down on this. This is the Vigor data set, a large scale data set with 4 cities in the US. And we trained in 2 of the cities, and then you get this same area performance, which was, yeah, in terms of localization up to, yeah, 3 meters. Median, it's now below 2 meters. So we have some outliers that is making our mean localization error not so good. But with in terms of the median error, it's already getting more and more acceptable below the 2 meters. And we are having here a median orientation error of about 5 meters. By the way, here in 0 degrees, it's if you have um, a known pose, sorry, a known orientation, and 360 degrees that we are fully ambiguous so that we don't know the orientation. And so this is what I showed on the previous slides. Clearly, if you know the orientation, as I showed before, we can get somewhat better localization results and don't have to estimate the orientation. So only here in these bottom rows, you see where we didn't know the orientation in advance, we're estimating it that we reached this 5 degrees error, median error. Now, and if we go to a new area that one of the cities, the US cities where we did not train on, and we see these unknown aerial images, then you can see that the errors are somewhat higher than what we have in the original same area setting. This is a more challenging setting, and that's true for all the models and everything that was reported in the literature up to this point. We can also do experiments on the Kitty dataset where we could compare to many other methods. And you can see here, again, we now reached median error below 1 meter for the first time on this benchmark. And also you can see in how many percent of the cases did we have an error below 1 meter. It's actually in 97% of the cases, which was much higher than all of the previous methods at that time. You can see here on that data set we reach really low errors in terms of degrees orientation estimates as well. Here's some more results. Here we tested something on the Oxford Robocar dataset. So this is an animation, and I want to stress this is single frame only. So we have here a limited field of view input image. You can see here the car is driving through traffic. There's all kinds of other obstacles that are not seen in the area view, but our network has learned what is important to match you. So you see here the red regions. Sometimes it's a bit more ambiguous, so it grows a little bit. But in principle, as long as our yellow star is on top of the green ground truth location, we're doing a good job. And now here you saw the case that I showed in the beginning with the road work, and we can see the buses. And sometimes we also observe that when there's a lot of traffic and our view is very much blocked, you're just looking at the back of a bus, that then the uncertainty grows, which makes sense because you really don't know where you are if you're just seeing the back of a car. And sometimes also these kind of repetitive street structures, you see sometimes extra modes show up. There's a bit of ambiguity, but overall, all these single frame results are doing very well. And clearly, if you would filter, also include some temporal information in here, where you take your knowledge from the previous post into the next post, then you could make this error much smaller. I think it's nice to see that we're not really, the network has learned to ignore the non-relevant information of the dynamic objects and only focus here on the static structures. So in conclusion for this paper, we are seeing a lot of work happening here in this cross-view pose estimation, every time now getting it more fine-grained, where we have this rough setting of this localization prior. And whilst all the work, well, I didn't really present this, but our original work only did localization, we are now also looking at orientation estimation. And I think the right way of doing it is not to treat this as a regression problem, but as a multimodal prediction problem where we can have multiple ambiguous locations expressed in our outputs and then use maybe some temporal filtering to resolve those ambiguities. And on some of the data sets, we're now starting to see sub-meter performance, although some other data sets are still more difficult. But clearly, if you would fuse this together with IMU information, with maybe visual odometry, wheel odometry, and then integrate this into a full framework, then the localization accuracy would be even much better, even though we're not using any, or we're just using a very rough GPS estimate in this aerial view. How am I doing with time? I think it's for me hard to see. I still have some time left, I believe.
Yeah. Maybe we quickly go through this.
Yeah, okay, so I'll try to go quick. So our final paper is the final paper that I want to present is the one that I just presented at ECCV in Milan. So this was a collaboration with my former PhD who's now at EPFL, so Simon, but also Yu Zhao from Shanghai and Shanghai Tech now. Before she was at the Australian National University, and also Hong Dong Lee, also from the Australian National University. So it ended up to be a collaboration of 4 different labs. And here we looked at the problem of that I was pointing out before, that we have this gap or this performance difference between uh, estimating our location in an area that we trained on and when we move to a new area, this cross area setting, where we have not seen the aerial imagery before and where we're doing worse. And so this is this, for example, if I train here on New York with images and I have this fine-grained ground truth, I can do this supervised training and we can do really well for new ground level images, but on the same aerial imagery from New York. So we have this model that we trained here, but now we go to Chicago, we have new aerial images and new ground level images. And what we see in practice is that these models become much more uncertain, so much more the red heat map here, and therefore also more prone to errors where we're selecting a wrong location. So there's a domain gap here if we just take this model and apply it to this new city. So our goal is to say, can we improve this localization estimate, but we don't want to do just more supervised training. I mean, that will be the easy way, but can we use this without these fine-grained labels, just these examples of this ground level image and this aerial image? Can we make this model better? Because, yeah, collecting this fine-grained ground truth with this high-quality GPS is expensive, but just getting rough examples of street level images with corresponding aerial images without exactly knowing where this street level image was collected, that's actually easy. So we want to use this noisy information where we just know these matching image pairs, but not the fine-grained location, as a way to fine-tune our model and doing some knowledge distillation and create a new model that is much more accurate on this new location. Okay, so this is our objective. Can we use images of the new area without the fine-grained location information to adapt our already trained model? And for that, we make a few observations. First is that the direct generalization, so directly applying the trained model, leads to this high uncertainty. There's a lot of outliers in there because we have these extra modes showing up. And there's also some more general uncertainty around the location. But we also noticed that a lot of the state-of-the-art techniques predict this heat maps. So this is this not doing this regression, but having this multimodal output now, and also coarse to fine approach. So one of the methods is the paper that I just presented, the PAMI paper. So where you have different levels of granularity in which the location estimate is being constructed. So we are using these ideas and trying to define a knowledge installation strategy that is using these observations to make something better. So the first thing is that we're going to use the model trained on, let's say, New York as our teacher, and we're going to use it to supervise a new version of itself that we're going to optimize a student model that we want to train on these image pairs from the new location, say Chicago. So if we just train our student on our teacher with the same output, of course, how would it ever improve? If you just show the model the same output it predicted before, it wouldn't do anything. So we have two insights. One, we can use the high level predictions of the teacher to supervise the student also at these lower level heat maps. So these intermediate levels, because we're following this coarse to fine strategy inside these models. We're using the finest level teacher to supervise also the lower level student models. And the other point is that we're going to say, let's take the teacher's output, even though it's multimodal. Here we have these different modes. We're just going to select its best mode, its most confident one, and only pretend that that is the correct pose. We're going to turn this into some sort of a pseudo label. We're going to ignore the other modes and just present the most confident mode to the student. So we're just going to pretend that the teacher knows best, which is not, of course, always the case, but we'll see what we can do about it in a moment. So we're going to train our student model using this fine-grained pseudo ground truth that we created from the images on the target area, the pseudo ground truth from the teacher. Now, that by itself doesn't really solve everything because maybe there are multiple modes that are likely. So here we saw the teacher, it predicted maybe this one mode and this other mode, and it took this one location as the most probable and created pseudo ground truth for this one location. And then we fed that to the students. But we can treat the student as an auxiliary model that we're going to use for outlier detection. So we're going to take a look at the difference between what the teacher predicted and now that the student that has seen now all these examples from the teacher with this ground truth and it's looked at all the samples in our new area, it might also make a prediction now for the same location. And having seen everything from our new target area, the Chicago area, we might observe that the student actually predicted a different location than the teacher. And what does it mean? Well, we don't know which of the two is correct. So the teacher might be wrong. It might also be that the student is wrong. We just know that this sample is unreliable. And unreliable samples we want to throw out. We only want to keep the samples where both the teacher and the student agree because those are most likely to be of high quality. So we keep the top something percent, the top X percent of most consistent samples. The idea is we take all these samples. We apply our teacher model from our new target area that we're interested in. We take a look at what the teacher predicts. We use that to fine-tune the teacher to create this auxiliary student model. We make the students also predict the same locations. Now we compare the locations of the student and of the teacher, and we drop the ones where they really disagree, and we only keep the samples where both student and teacher agree. Now we can filter out only those samples and say, here we trust the ground truth generated by the teacher. We also only keep those aerial images. So we've reduced our set, but we now have a better quality pseudo-labeled ground truth set. So we can again train a new student model by fine-tuning the teacher, but this time only on this reliable set of images. And that student model is of higher quality. This is a reliable student model. We can see that we have reduced here by 12, 16, or even 20%, depending on what metric we're using, on two different baseline models. The error with only a little bit of fine-tuning, and it's actually very lightweight to do this fine-tuning, but without any fine-grained ground truth. So just exposing the model to this information, you can see we can really get relatively for free this improved model for our new target area. So we have adapted it. And we also show in our paper that if you use sort of a generic domain adaptation technique that uses entropy minimization, just doing that, it doesn't work. So we really needed something that was tailor-made for this setting. Again, finally, and then I'm done, some qualitative results. So here is an image from the target area that we have not seen during training. The teacher predicted this wrong location. Our true location is over here. But now our student, after the fine-tuning, found here the correct location by just exposing it to these samples. Here's another case where the teacher was completely wrong. It thought it was over here. It never seen this kind of environment. Well, the true location is over there. And there wasn't, yeah, the teacher did not even consider this. There's no red heat, so no density being predicted over here. But after adaptation, our student model does realize it's likely to be here and even the most probable location. So we also improved there. Basically, we have learned to better disambiguate the modes and also even create new possibilities that the teacher did not consider before for this new location. So that wraps up my presentation. Here are the 3 papers that I presented, including GitHub links and archives. I think the GitHub page from our ECCV paper still has to be updated because I think Simon is very busy with the CVPR deadline, but it should be up there soon as well. And our other models, including checkpoints, should be already available on GitHub and the papers as well. Thank you very much for your attention. And if there are any questions, please let me know.
Yeah, thank you. Have any question from our audience? Yeah. So sorry, we do not have microphone today, so maybe just speak louder.
Yeah, I have a question. Should I maybe
I think we should. Sorry. Actually, we have an audience who has the question. I just opened the camera and you can see us. Right. Oh, thanks, Professor.
Okay.
Yeah,
Sure.
let me come here.
Hello. Hi, Julian. Thank you very much for a very nice talk. Yeah, I have a question about one of your results. I think you didn't have any slide numbers on the slide, so I don't remember which one. It was one of the first slides with results, and there was a failure case there about the direction. And
I'm
yeah.
going back to the slide. Maybe you can say stop. I don't know if you can see my slides still.
Yes, I can see. Okay, it was a slide where you had four cases, and the last one was a failure case with the direction.
Let me look it up. This one, I think. Slide 21. Yes.
Yes, I think this one. Yes. So quite surprised actually, because the let me see, here is kind of covered on the laptop, but Yeah, it's actually, I was quite surprised. So because the yellow is your yellow is your prediction, or yellow is the ground truth?
No, green is the ground truth and yellow is our prediction.
Yellow is the others.
Okay. So, but the green here, the ground truth actually points in a different direction than all your predicted arrows, right?
Yes.
So, okay, I see. So that's basically the direction you're predicting is 180 degrees here from the actual case, right?
Yes, so it is a failure case, right? We included it on purpose as in, okay, the method didn't magically solve everything for us. So what's interesting to see, I think, is that you can see from the red area. I hope you can watch the. I'm not sure if you can see what I'm pointing at. So from the red, you can see that there is ambiguity along the road here, right? So the road structure, it knows it's somewhere over here, and actually the location that it picks, the most probable locations where we put our yellow marker, is very close to the green position. So in terms of the in terms of the location, it's actually pretty good. Although we can see it was a bit of a gamble because there's a lot of uncertainty here. But indeed, the orientation field was wrong. And that's because we don't really predict a distribution over the orientations, right? So we do have a spatial distribution. This is what we see with the red. But for each spatial location, we only allow the model to predict one orientation. And that means in this case, the model has to choose for each location, is it looking in that direction or in the other direction? So for these kind of cases where that's fully 180 degrees ambiguous, yeah, the model picks something, right? And it could be wrong. So
Yeah.
we get a distribution of orientations if it's coupled to these different locations. Each different location has a different orientation, and we have different locations, then you also have different orientations. But in this case, it's just for this correct location, the wrong orientation, then we don't really solve it with this model.
Okay. Yeah. Right. So thank you for the explanation. So it seems that maybe 180 degrees is a more likely failure case than, let's say 25 degrees or something like that, right? So because it's just, yeah, predicting the wrong direction. The
Yeah,
opposite
so this is
direction. Yeah. So
sorry to interrupt you.
no worries. Yeah. Yes, we've done some work. You've looked at your paper, and my student has done some follow-on work as well. So I think this is very interesting, and it's I'm really impressed how well it works. It really works well. Yeah.
Yeah, there was a lot of engineering work in, like, okay, we knew it's the level of details that we did not have that in the ECCV paper from 2022, right? So we tried to get that in, and how to make it work was quite hard. But yeah, I think Zeman, my student, did a great job here. Maybe I just wanted to pull up this result with the orientation where you see the mean and the median error, and this was also always a bit of a discussion. I think the mean error is way bigger, and that's because of this 180-degree kind of ambiguities, right? So it pulls it up if you just take the error and you take it. But if you look at the median error, then you can see, yeah, that's because of the skewed error distribution that the median is indeed much better, and that's true for many of these cases.
Yeah.
But yeah, I agree. I think thank you for the nice comment. It's nice to hear that people are looking into it and trying it out as well.
Thank you.
The,
Thank you.
the
Yes.
approach is simple. Yeah. Thank you.
Great talk. Thanks.
So maybe one more question from our audience. Yeah. Do we have any question? Yeah. Okay, good. Maybe I ask the final question. So, the ground truth is just like the optical flow. So you have the direction for orientation of the every part.
No,
Uh,
no, we don't. So also this is a good question. Also, thank you. So at training time, all this model is trained supervised. So we only know the orientation of the true location. So when we train this, let's see, when maybe this is the no, sorry, let me go to this this image where you see the whole network. So here we have the input on the left, right, and the output on the right. And we only basically put a cross entropy loss here on the distribution itself, so we know the true position, and we also have a loss on the orientation here. So we know for the true position what the orientation should be. So we don't define what the orientation should be at any of the other locations, but the network is free to come up what it thinks is the most likely orientation for those locations, because the whole thing is convolutional. Right? So the convolutional filters will make predictions for all of the locations. But we only supervise it at the true position, and therefore it still learns to match the visual information and correlate that also for all these other locations.
Sure. So currently it's the visualization. We get the results. We're using the particular result to do the visualization. So here you show the visualization results, right? Okay, I see.
Exactly. But and actually one final maybe comment on that is that in our view, what we notice is that these arrows are only robust and really reliable also at those locations where the location information is meaningful. So the arrows outside where you see there's no heat map, it doesn't really match that location. The arrows are also not very good. They tend to just do noise stuff, and if you change a little bit, they completely change. They're only really robust and meaningful at these heat maps, where the heat map is giving us a high location probability.
Yeah, actually, I see your animation. You just turn around the orientation and see the round, the corners. They do not change orientation. You only change the the center, the red part, right?
Yeah, they should change very slowly because everything is fully, but you see that, yeah, they're not stable. They're just turning into random locations. It's only here inside the red stuff. And we did some more experiments in the paper. But if you look at the moment as the car's driving through the streets, then you see that the arrows really adapt to the location as the car is seeing a particular part of the street. But if it's not seeing a part of the street, then the network is just predicting the driving direction in the streets only based on the aerial information. But it doesn't. It just becomes a sort of a prior that it thinks is reasonable for the street, but it doesn't know because it's not seeing it.
Yeah, sure. Thanks. Yeah.
Thank you.
Thank you. So I think the time is up. So maybe we change the next speaker. Yeah. Thanks you, Julian. Thank you. Thank you very much.
Thank you very much for inviting me. Have a great conference.
Thank you. So next speaker will be our Professor Javen Shi, and he is the founding director of the Causal AI group at the University of Adelaide, and one of the director at the Australia Institute for Machine Learning. And he do a lot of great work for the causal learning. So let's welcome. And maybe we need to do some technical things to share the slides. Oh, hold on. I still need a USB to insert. Sorry. Maybe copy. To the desktop.
Yeah.
Okay.
Otherwise, it will be slow.
Okay, sure. USB driver is not very stable. Okay. Maybe the slides. Fine. and change to the yeah. Sorry, I checked out online. Maybe we stop sharing, so we need to share again. Sorry, take a moment to share the whole screen. Yeah, good. Sorry, our online friends, can you see the slides? Right, I just play it. Right, I changed to the duplicate.
Yes.
Okay, thanks. Thanks. Let's welcome the Professor Shi. Okay. This is for microphone and the camera, and this is for the offline in loader. Yeah. Sorry.
Right.
Sorry, the screen is not very stable. Maybe
I can just use that, right? So
no, you still need to use this slide to click the mouse, and this is for sharing.
okay.
Thanks.
So let's say okay, that's works. Hi everyone, I'm Javen Shi. So okay. This I guess is mostly for people online, right, to hear me. Because for people in the room, it'll be fine. So what is causality, right? Most of the deep learning stuff, right, we're doing are correlations, are not causality. So can we do better? Maybe. So there are forms and there are formulas. So a rock has a form. Human body has a form. Even a salt has a form. That's called a salt form. And all forms are forever changing and non-stable. So for your human body, every 7 years, all your cells actually have completely changed. So you become a new person. Right? No single cell is the same after every 7 years. Okay. And we're living in a time that AI is making wonders. Thus, going to change not only in the production, but the social structure, which is going to bring a lot of disturbance, distress, opportunities too. So all the things you can see and you can smell, you can touch, they are forms and they are changing, and they're changing faster than before. And the way of change is causality under the disguise of an causal effect. Why is that? Because when you think about what is a cause and what is its effect, it is always about if you change something, what else change with it, right? No exception. Do not trust a decision that is made only on correlation. Right? Think about all the AI stuff you have been doing. If they are all about correlation, then if you want to make an important decision in the future, think twice, right? So we're going to present to you a scenario where the data actually have no noise, has no distortion, but you cannot make the right decision if you only use correlation. That's known as Simpson reversal and paradox. So the first example would be reversal. And you could just say the second example. So two examples combined is called a paradox, Simpson paradox. And this is a medical case, so it's important, right? It's about your health, and you die or you live on. So it's not something you can dismiss. You have two treatments, A and B. Doctors would actually normally scan you to say, do you have small stones or big stones? And then they decide, right, to give you treatment A or treatment B. So those are the recovery rate, those numbers, right? So if you observe on the stone size, look like treatment A is better, right? Recovery rate is higher and it's bold-faced. If you don't get to see the stone size, look like treatment B is better, right? It's bold-faced. So you have the reversal effect, right? Condition on the stone size, you get one answer, and without knowing the stone size, you get the other answer. The question for you, right, is which treatment is better, regardless knowing the stone size or not. So the choice is actually does not depend on you get to know the stone size or not. There is an absolute truth in this case. So can you tell me which treatment is better? Any guess, any answer? People online, you can speak up if you want to, because I can't check your text.
Looks like A.
You think A is better? So anyone believe B is better? Put your hands up. So we get a no one. Okay, then B is better. And anyone believe A is better? One. So now we have people who don't put hands up, right? So not deciding. In this case, well, A is better. So
Quick question.
okay.
So looks like the number for separately for both cases are better than treatment B, but how can like the number for both from treatment B is higher than treatment A actually?
Yeah, without knowing, right? Without knowing, which is the marginal. The marginal, if you look at the marginal distribution, B will look better. So in this case, it's because it's more when doctors say if you have a small stone, they think you probably don't even need a treatment. You just drink more water, you jump around, and you'll be fine. So when small stone, they often give to the treatment B is a cheap treatment or almost like a placebo effect. It does nothing, just self-recover. Treatment A is a comprehensive. You take some drugs and maybe some injections, even surgery, right? And doctor often give, if you have large stones, they do a severe intervention. So, but because it's a much harder case, so even with the best treatment, the success rate is lower than if you have a small stone that you don't even need a treatment. So the reversal effect happens because the doctor, they send most of the small stone patients away saying, you just do a cheap treatment, right? Or do nothing, you'll be fine. So more easy cases went to treatment B, so that number look better, right? If you ignore the condition. But if you know the condition, then in all the cases, A is better, because A is a more comprehensive, more expensive treatment. So second example, I purposely keep the same numbers, right? So you cannot say numbers has changed. No, the numbers do not change. Only the storytelling has changed. Now you have a heart disease drugs, right? Two of them, drug A and drug B. You have a blood pressure, low or high. Now you see the reversal again. Now tell me, who believes drug A is better? Put your hands up. You believe A is better? Okay. Yeah, same numbers. Who believes B is better? Put your hands up. B is better. Okay, 2 of you, 2.5. B is better. But why? Because we've just learned A is better, isn't it? Did we learn from the kidney stone case? Right? Because from kidney stone, looks like you always want to believe the conditional probability. But why in the heart disease, the drug problem, you cannot trust, cannot believe the conditional probability. Now, if you're one of the people who only depend on correlations, now you don't know how to decide. You would never know whether you get it right or wrong. I've seen a lot of statisticians who baffled, right, who don't understand this. Right? Some have white hairs, they still don't understand this. You need to correlate, you need to go beyond correlation. So here's why. So if you look through the causality point of view, the mechanism is different, the causal DAG is different. In kidney stone, is a doctor decide to give you easy or more comprehensive treatment based on your stone size, right? So stone is the cause to both treatment and to the result. In the drug case, it's not doctor deciding on your blood pressure. It's the drug. Give you two different drugs. So the drug that works is the drug B that works by lowering your blood pressure first. If you can lower your blood pressure, then the chance of you getting a heart attack is much reduced. But what does this do? Why you cannot condition on the blood pressure? If you condition, if you observe the blood pressure is blocking its causal influence, which is saying, I know your drug B is great at lowering my blood pressure, but now I do not allow you to do it. Right? If I disable your functionality on lowering the blood pressure, can you still reduce heart attack? So in this case, you should not block it. You should not observe it. Right? But how do you know when to do what? Well, embrace causality, right? Doubt correlation. So two examples combined is called the paradox, Simpson paradox. And paradoxes actually are not troubles, they are treasures. They are showing the ceiling of your understandings. Paradoxes are relative. They're not universal to everyone. What Simpson paradox is a paradox to people who only understand correlation, but not a paradox to people who understand causation. So you can embrace paradox in your life and use them as signpost to point out where you can improve, break the ceiling of your understanding. A few other key messages that hopefully can help your research and your life. So humans are 5 sensory beings, right? So we rely on our vision, our taste and touch, and other sensors. And the stuff, you can use a scientific device as well, right? But there are always things, forms that are beyond your device and beyond your sensors. So you have to make, when you design a mechanism to make decisions, you have to embrace, you have to accept there are always things you cannot see, detect, or measure. But you still hope to make the right decisions, don't you? A good news is the causal AI actually can discover a lot of the latent variables, right? Not all of them, because it's always going to be something more that's unseen, that's unrecoverable. But yet, there are ways and there are hopes for you to make the right decision if you are open to this. The second message is sometimes you can behave much lower than your normal capability. Don't be too confident, too cocky. It can be your vision or your IQ or EQ, right? But the good news is that's temporary. So lower your ability is often temporary, not forever. A famous example is a basketball gorilla example. So they get a lot of people from top universities in the US. So they are not idiots, they are actually intelligent people, right? To watch a video of people playing basketball. And the question for the audience was to count, to answer how many times the players pass the ball. So that was their task. So they were all focusing on that. But in the end, there was a question asking all the smart students, right? Was there a gorilla in the basketball court? They all said no, right? It's like, wait, there's a human playing basketball, right? And we count how many times they passed. No gorilla. And then replay the video. There was a gorilla passing by, right? So were you blind? No, you are not blind, but temporarily your ability was lowered. When you are attracted by something, actually you would not pay attention to the other things. So also that's about vision, but also can be about your EQ as well. If a friend of you or coworker for you attacked you, right, verbally, most people will just react, right, fight back. And later on, you may regret what happened. So were you always that harsh? No, you were not, right? You were often better than that. But when you were attacked, your EQ temporarily would be lower than your normal standard. Mind is a choice maker. So you're always making choice. And that's related very well to reinforcement learning. Right? You can use that for your drones if you like. People often mistaken about when they come to your daily lives, what things happen to you, they mistaken what is the cause, what's the condition. What you can do is mostly about yourself, right? You can change your belief, you can take your action. You cannot often force other people to do what you want, to manipulate. If you could, you're powerful, but you're kind of negative, right? So I'll give you some example, right? That your mind is choice maker that actually helps you, but don't mistake what is cause or what is condition. If you believe young people should not eat food in a dining table when elderly were present, and if you believe young people did so, you'll be upset and angry. Then one day when that happens, you get upset. Would you believe the young guy who disobeys the social norm be the cause of your upset? Is that the cause? Or that you believe was the cause? Another example is maybe you are a person, you like shiny days, right? Most people like shiny days. Some people like rainy days, right? So if, say, yesterday, if it was raining, would you blame sky, blame earth, blame the climate? Say, well, that was a bad day, right? The sky or the God was not playing nice, so that I had a miserable day. Would you think the weather was the cause? Or was the belief was the cause? If this happened to another person who believed, actually, raining day, if it's not too heavy, raining day was nice, right? Cool, fresher air, right? And they want to celebrate, they had a good day. Then think again, which one was the cause? Was the weather or was your belief? Can you change the weather, by the way? No. So in causality, there's not only cause and effect, it's also condition, right? So in Buddhism and in other religions, they have three parts. They're not just two parts, not just cause effect. You have condition. And often the conditions, the events happen to you. They can appear to be random, and they are the catalyst that if you can learn from it, then you benefit. If you don't learn from it, it repeats, right, until you learn from it. It's up to you, right, to realize what is the cause and to make the right choice. And there's also a difference between instinct and intuition. So instinct is from the bottom up, is for survival. So if you suddenly jump away from the road, from the traffic, avoiding a fast approaching car, that's instinct, but survival, right? In your daily lives, if someone angered you, is often not about survival, but you often react, right? Eye for eye, right? So what is intuition? It's from top up, is inspiration, is some ideas you didn't think of, you didn't had before. And that's actually a blessing. That's very good for you. It's not about survival. It's not about reproduction, right? So there's a huge difference between them. Don't mistaken intuition with instinct. We want to have more of intuitions. And luckily, right, if you're females, you're naturally born with more of the intuitions. That's great, right? No learning comes without desire, or maybe called intention, without intention and persistence. You can roughly relate intention and desire with reward function, reward in reinforcement learning. Not exact the same, but you can relate. We're going to mention more about that later. And if you work in RL, you would know normally it would take about 1 million to 10 million episodes for RL to converge, right? And now we have ways faster than that, right? But still, learning takes persistence, right? It is not you try once, then you build that become building to you. No, right? Sometimes you blend the life, the hardship or upbringings. Well, think about whether you've been persistent on that or not. So when you see correlation is not even real, right? It's a mental construct, right? It's like a curtain that what is real is something bulge up behind the curtain. That is real, not the curtain. So whenever you see correlation, it whispers causation. So there's something called a common cause principle. If you say A and B are correlated, one of the three things happens. Either A equals B or B equals A, or there's a common cause that causing both A and B. Is this principle absolutely correct? No, but it's useful enough. One example would be shark attacks correlates with ice cream sales. But if you ban ice cream sales, it does not reduce shark attacks, right? And if you are greedy ice cream owner, if you get more people bitten, doesn't increase your sales, neither. Right? So what link this to is temperature. Temperature is a common cause. When temperature is high, more people go swimming, get bitten, and more people go buying ice creams, right? And also you may joke about it, right? You would never think about shark attack and ice cream and utilize one or two. Well, think again. So there's a famous Pfizer $800 million example. So they find out one type of a cholesterol called a DHL correlates positively with your heart condition. So they figured, okay, if that's the case, if we invent a drug that boosts your HDL, that probably will improve your heart condition. So they invest $800 million in it. The drug it did work for increasing your HDL, but doesn't help heart condition at all because that's a correlation. It's a spurious correlation. It's not causation. So causality brings you essentially three powers. First, deeper truths. So causation rather than correlation. So you can navigate. You know how to make the right decisions, choices. And also you can embrace the unknown. You can discover some of the unknowns. Second power is realize you are the master of your fate, right? You can change things around you. You can proactively to change, to intervene, and to shape the future that you desire. And the world around you is not just passively happen to you. You are not just you can say abandoned poor person in a harsh jungle. If you believe so, you would become either a slave to the jungle or the biggest bully in the jungle. Either way, it's not nice. Once you realize your power, you can turn the jungle to paradise. Right? If you see somewhere have a high crime rate, it is not about to capture, to be harsh on the guys who did the wrongdoings. It's about to change the soil. right? Why this happens that often at the first place? The third power is a holistic view. So you can see all tasks, all data as one. In a way, that's what actually ChatGPT does. So it stitch more at the effect level. So if you envision, right, with your mind's eye, envision an ocean, the top of the ocean is very wavy. That's the effect, right? It's violent, and you need a lot of data to stitch task and data at the effect level. You need trillions, right? That's why large language models are so hungry. Then envision the deep bottom of the ocean. It's calm, right? It's unchanging or not changing that much. If you stitch at the coarse level, you don't need much data. You can do data adaptation, domain adaptation, right? Generalization, much easier, much better. And that's what we are working on, right? And by the way, causal AI actually is compatible with large language models. You can have both. So here is a quick example, one-page example, crash course for causal AI as structural causal models, right? You have the variables that you're interested, called the endogenous inside, right? So once you're interested, endogenous variable, x1, x2, x3, anything you're interested, right? Your profit, your temperature, your yield, growth, right? Health. For every endogenous variable, you have a exogenous variable. It means outside variable, background, word background variable. Some people call it noise, but it's not actually noise because it carries information. It's meaningful. So whatever on the right-hand side, they are the parents. Whatever on the left-hand side, they are the children. They are the cause. They are the effect. So from ACM, you can draw a causal diagram, right? Like the one below, right? And when you do intervention, it's fundamentally different from conditional probability. Because if you do intervene x2 to make it to equal to 2, you're chopping off its parents link, right? You get a new probabilistic graphic model. You get a different distribution. That's why people often cannot do well on distribution shift, right? If you use the old one, the model you learn from the old data, you adapt to the new. Of course, it doesn't work because distribution has changed, right? You need to understand how it changes. Of course, causality can help. So that's the intervention. And intervention is not the same as a counterfactual. That's a common mistake. Counterfactual, to counter a fact, it means you already have a fact, right? Something already happened. So if something in the past already happened, you observe it. Then you want to counter that. So counterfactual, you have two things to do. Step one, time travel to the past. Whatever fact observation you made, you travel back to that world. How do you do that? Remember, there's a what background stage variable, the n, right? N1, N2, N3. If you recover that, you can reconstruct the world in the past. You navigate, travel back to the past, then you intervene, right? And intervention normally, by default, is about you intervene now and see the different result in the future. That's not a counterfactual. So a famous example would be if Hitler died when he was a kid, well, World War II still happened, right? So you have to travel back to that World War II, right, before it happens. It's not about someone named Hitler as a kid died today. No, it's not about Hitler died. Someone named Hitler died in Gaza. No, it doesn't help you. No, that. So here is, if say, what question was what x3 be if we had x1 be 2 instead of -1, right, as we observed. First step, travel back to the past world. So you recover N1, N2, N3, right? 3 numbers. Then you put it into the ACM. Then you put the new number, x1 you wish to be in, and see the result. That would be 32. Okay, that's the answer. there are only two fundamental questions in causal AI, which I call first forward question, right? Is you want to answer, if you change something, what else change with it? If you borrow some money to buy a good house in Melbourne, would the value increase and would you not go bankrupt? Would you be okay, right? You can answer all kinds of questions, right? It's a forward question, right? But the problem with that is you have an infinite, many possible sequence of the interventions you can do, right? So, but you cannot exhaust all of them because it's an infinite many. And also, you need to uncover the underlying causal mechanism first. That's why often you do causal discovery first, you do causal inference, and they are all forward questions. They're all about, if you do this, what happens, right? The second question, called the reverse question, is actually more important. That's what my team is focusing on. My team maybe is maybe the only team focusing on this reverse question, because we named it, we proposed this question. We believe that's more valuable for you, right? If you have a dream, right? If you want to have a better future, if you can see that future, and you realize you have limited resource, could be time, money, talents, what are the optimal sequence of interventions that you can do so your dream in the future can come true? That's the important question, isn't it? For everyone, AI or not, right? That's the question you want to ask and you want to be answered. That's why my team is focusing on that. So for the forward ones, sometimes you have backdoor, often you don't have backdoor, and often your backdoor is not observable, somewhere but not observable, so you cannot block it, you cannot adjust it, so make it useless, right? Often it's useless. Often you don't have front door, so it doesn't work for you, right? Often, those are the classical ones, right? People know that. Sometimes you have the instrumental variable, that's more useful. Often you don't have a strong IV, but a few weak IVs will actually serve a strong IV. We'll show you more, right? It's a bit more useful. So you want to know about the effect, right? The treatment is X, the effect is Y, right? You want to see how big is the effect from X to Y. And you understand there's an unobservable, a latent common cause C. And the IV is the Z. I'll give you one example so you can understand. See, if my friend Don wants to sell his guitar to me, right, for a price of 20K, quite expensive guitar, right? Then he's playing his guitar. It sounds nice, right? But I always happen to observe there's a CD playing at the background too, so I'm not sure that nice 20K sound of the guitar is from his guitar he's playing or from the CD. It's quite common, right? Especially in Asian countries, right? The singers don't always sing, right? So it's so how they do it, right? Is to say, well, don't stop playing the guitar. By the way, stop the CD as well, right? So no sound, silence first. Pass on the guitar to me, I'll play it. If I'm very good at guitar playing, then I'm a strong IV. I play it, so I know, okay, this sound is actually like 20K guitar. It's great. I'm not a good guitar player. I can play some notes, not all ranges. So I bring other friends along. We are all weak IVs. I play maybe the low pass, some play the high pass, some people play middle range. So a few IV together can serve as a strong IV. And you can see the algorithm as well, right? The blue part are the additional components if you use IV or not, right? So it does make a difference. What if you don't have IV? Is that even possible? Often you don't have IV, right? Believe me, in real applications, you don't. So then what do we do, right? Is that even possible to recover unknown causal mechanism? Let's give you some cold water to wake you up first, all right? So in many cases, it's not possible. I just give you some example to demonstrate and also the proof, actually, with one counterexample proves that in general, no, you cannot uniquely recover the latent variables. The reason is that, say, just simple maybe MLP, say, from Z is the latent variables, right? You have, for example, 2 of them. You have observation X, could be a picture or text. From Z to X is a powerful MLP, which can observe pretty much all linear, nonlinear mappings, right? Those 3 models below, right? They have different structure. One may have edge, one don't have edge between that, right? They have different factors, but adding an edge or not, adding a factor before the vector, the latent variables or not, actually all the changes can be observed by your powerful MLP, which means all the 3 different models would actually can produce the same observation, which means from the observation alone, even multiple observations alone, you cannot uniquely recover what was latent. So to uniquely recover and to be able to prove that you can recover this uniquely is called an identifiability problem in causal AI. So for them, very important, you have to prove it. Most often, they have to prove the math before they do experiment, right? So the bad news is you can't in the examples, right? If in general setting, you cannot, right? But changes make it possible. Changes are not your enemy. They are blessing. Okay. If you realize so, right? You can get a lot of help from changes. So you can have the graphic models, right? You can have the more fancy version. You have the domain index or actual helper variable, U pointing to N and then to Z and to X, right? You have more complicated version like this. We kind of have we have to apply some restriction to it though. Right? So, but before so we believe we welcome changes. But before our sort of school come into causality community, it was otherwise. It's often believed you need to have sparsity or pure children. It's more like if you don't change much, then we can decide you. But you know, change is always happening, right? For all forms. So accept it, right? Why deny it? Especially when it actually helps you. So if we have, just give an example, right? If Z1 pointing to Z2 like that, can we uniquely recover those variables? Well, yes, if we can remove the naughty ones like 2 and 4, because those are the ones that don't change with the domain, with the distribution shift, right? Or with your task, or with your subpopulation, right? Those can all be your U. But if they change, then we know, we can decide them. So we have a paper on that for the linear case between Z, of course, from Z to X is nonlinear, right? And people say, well, we want nonlinear ones, right? Nonlinear ones are more powerful, so we have a polynomial one version. Then people say, yeah, we want an MLP. Sure, we have an MLP version too. So simple, quick quiz, right? So by now you realized embrace change. Change is not your enemy. With enough changes, you can recover latent variables. Right. Question is, okay, if you have this domain shift here, but your Z2 doesn't have the U on top, can you learn an AI model that perfectly adapt to changes? Actually, yes, you can. But how? Well, think about it, right? This is one example of our within my group, the causal AI training. So, and some people believes the bias. If the bias in your data, the only way to fix it is to remove the bias in your data set. Right? They often say garbage data is important. Data quality quality, garbage in, garbage out. It's not true. The AI model suffer from the bias is only if you use a statistical model, because all stats model is a summary of the data. So whatever in your data, is seen in the summary too. But causal AI doesn't suffer from it. So here, with causal AI, we can actually discover and disentangle the content variable that decides the label, the style variable that contribute, and not to the label, but to the observation alone. So, but why does this help? In this, when Amazon did online recruitment, and they realized they were in trouble, they use AI, they hired only men, no female at all. Right? So they have the gender bias. And also when face recognition software was trained on the US soil with US data, they test on the Black congressmen. All of them classified as criminals, right? Because they have black skin. That's all because of bias in the data set. Can they be done without removing bias? Just you build an AI model that has immunity to this bias? Yes, you can. With my AI model here, you are first to get to the content, which is a colorless man or person. So you will not decide he's a criminal or not based on his skin color at all, without fixing the data. When you recruit someone, you will become a genderless, gender-neutral person. So gender would actually not have an effect in your decision-making. You are immune to those bias. We have a paper on that, but let's move on a bit more. So the parent, image to image or image to text parents, they actually can be seen as a before-after effect for causality. It actually helps you to learn better models. And that is actually the reason why clips work so well. So we have a paper for that too. But to pair image and text is hard because you have to do quality control, right? Whether the text really describes what's in the image. It's not always the same, right? Or align well. But think about this. What is, you mean a label of the image is a word or text, isn't it? That's a label of image. Then what, if you generate new text, what's the label of the text? Still text, right? So, which means if you generate whatever text you generate, you already have the labels. So you can just do pairing for free without the quality control. That's what we call it collab. It works a lot better than clip, okay? And you don't have to remove all correlations, right? Don't trust the decision only on correlations, but you don't have to remove all of them. In this case, is two domains, image and text. Between them, it's very hard for us to decide is that image is the parent of the text or the text is the parent of image. So in this case, we don't have to decide. We can still uniquely recover the content variable. Okay, now moving on to the more interesting, more important question, right? How do you change your fate? Right? Not only for your research, but for your life. Don't you want to have a better life? Right? Isn't the world, the society is so convoluted already that the harder you're working, the more trapped you feel you get in? So, well, this is different from reinforcement learning because reinforcement learning is not about changing the environment, changing the fate. Reinforcement learning is adapting to the environment. But reinforcement learning can help. You need that as maybe foundation. So often in RL, you have an agent that explores, interact with the environment. And this is fundamentally different from supervised learning. For supervised learning, you need the answers. You need the right answers. The answer can't be 50% right. It has to be 100% right or nearly 100%, the best you can, right? But that's too demanding, isn't it? If you start a company, no one really knows for that company what's the 100% right solution to do it, right? Even the best entrepreneur don't know. They probably know for theirs, but not for yours. So the supervised learning doesn't really help, right? Does not cover reality. Reinforcement learning does. All it needs is the world give you feedback. If you did it right, you succeed. If you did it wrong, your startup company will bankrupt. Okay? That is very accurate feedback. That's all you need for RL. Then you will just self-improve. So you have typical MDP setting or PROM-DP, so the partially observable. The world is, of course, a PROM-DP plus causal AI on top of it, because you can change the world. You can change your local environment at first, right? The reason is PROM-DP is there's always things you cannot see, you cannot observe, and the device cannot capture, right? Often you play a game, the prize is not on the game board. So you have a reward function, right? What you often hope to have is expected cumulative reward called return. You have the probability for the trajectory. We're going to see two classical methods, then see our own method called highway graph, and then see how that may help you to answer the question, the reverse question, that how can you change your fate. So you have the J is the return, right? So it's the one you want to maximize. If you decompose it, so it has a problem, right? So it's policy gradient is like a company often build up the project teams, right? And then based on how successful that project, that team was for that mission, then reward team members based on how often you contribute, or how, that's a probability there. The log probability means that how likely you've been selected on that team, and then everyone gets the same bonus. Right? The problem for that is if someone who actually never contributes, but always know which winning team to join, he or she would be actually collecting a lot of bonuses, right? Despite not contributing. That's a famous credit assignment problem, and also credit assignment problem, right? In this policy gradient. Another problem for policy gradient is very calculative. And your mind is also very busy, so it's not going to be easy life. That's the algorithm, but skip that, right? Principle would be more important. This is Q learning derived from Bellman equation. So this is based on, is actually does, if you do it right, the planning is already included in retrain your mind and your muscle memory. So Q learning actually already have built-in planning. All the value iteration method that if they do it well, you already have planning built in. So that when you do it, you don't have to think far. You see something not in the real world, right? Not on the game board, but you know what to do, what to go. So that's the essence of Q learning. Much easier life, harder to attach to get. That's algorithm. I have a picture. So this is a picture of my courtyard. I have two courtyards and front yard and the massive backyard. But the courtyard is next to my study room, so I often see them. And it actually is not a nice tree for reinforcement learning. The tree branches are like the trajectory you can possibly try, right? What Q learning does, right? Q learning chop off your trajectories to transitions, right? T to T+1 transitions, and put in the buffer, and then to learn from those chopped off slices. So it's all about learning transitions. It's about how do you stitch the tree branches together, right? But can be happening at different locations because the samples you get from the buffer can come from 100 or 1,000 different episodes. They don't have to come from one episode. Whereas the policy gradient is always about from the same episode, right? So have the complete episode because I have to assign the credit to everyone, right, for that episode. You can also have MCTs, And we're going to see our algorithm highway. So what actually inspired us was if you drive a car and you know you can only drive normally, legally, right, along the roads intersections, right? You cannot easily fly, you cannot move or teleport, right? So you know that's a fact. Then you think about yourself as a reinforcement learning agent. Then why do you make decisions only about the car turning wheel inch by inch forward or not? You never actually care that much about those level of details, right? The car's wheel moving inch by inches, right? So that made us realize we can zoom out, right, with the bird view to look at the map, look at what are the highways, what are the roads, where are the intersections you can actually split. That's the junction point. That's the critical decision-making points. Whereas the daily habits of rolling on, moving your car inch by inch is not that important, right? So that's why we invented something called a highway graph. That's highly compressed your original state transition graph. And so normally you train on a lot of environments. It takes about 12 hours to train. And for hours, it takes you 10 minutes, 5 minutes, or 30 seconds to train and converge. And also, we didn't even simplify the world. We still interact with the real environment, but and you can see how nice the value, the return is like compared to other methods. And that's the algorithm, and that's why it works. The key reason it works is we do value propagation on the highway, right? We somehow move on. We're not getting caught by daily small troubles. So if you wish to change your fate, if you want to be able to answer the reverse question, a few things you can try. One is causal IL. The other is a dynamic treatment regime, right? But we're proposing the third setting. Right? Probably you can see that in a proposal in your paper that is better than the first two. In causal IL, you often have a causal model for the environment, so it's model-based IL. You can also have maybe a causal model for the agent. You can have both. Okay. And we have done a lot of applications. It's hard to find an application or area where I haven't done. So in agriculture, with wine industry, with wheat and shotgun and barley, discover energy material with AI. We won that at NIPS competition last year in December. So we didn't know that we can win. We just tried. Worked very well. So, and we used AI for wave and with energy harvesting. For mining exploration, we won that too. Dong is one of the team members. We did that for health. We did that for fintech and for education. So AI is the new electricity, right? It's everywhere. So of course it can help a lot. Right. But this is the most important question, right? People are waiting for, right? The applications, what's the past? What about the future? I guess most people, right, have the question, will AI and robotics replace jobs? Of course, 99%, 99.9% will be replaced. Some people may say, especially the government tell us, don't say this, right? The government tell us, you should say, every one job that AI replaces, it generates 1.5 jobs, right, for the future. And that's true in the transition. But in the end, no, jobs will be replaced, most of them. But are you really afraid of losing jobs? No, you're not afraid of losing jobs. You're afraid of losing income. That's a big difference. If I give each one of you $10 million a year, every year, for free, do nothing, would you not take it? Of course, most of you would take it. So you're afraid of losing what? Income. not jobs. Why do we have to work for income for the past few thousand years? Because there was no other way before. You use animals to improve production, right? You use machines, but they can expand human capability. But most of the stuff still need a human to control, to operate. And so the production, so society needs to design a system to motivate people for production. But now the time of AI, especially AGI, it's not just a multiplier of human. It's a replacer for human production. And production can be completely done by AI and robots. Then we don't need that system anymore. Why do we still link production with income? When robots does everything production for you, there's still a huge role for humans though. Human can live a life, enjoy life. Right? In consumer, be a nice consumer. AI cook very good food. When you taste it, you give feedback for AI. A terrible food or nice food. Good job, AI, right? Travel around. Be with your family and loved ones. Go chase your dreams. In the time of AGI, when production is not done and not necessarily done by humans, is the time humans will truly be free. Why do you have to work for a living? That's ridiculous, isn't it? Being born is already a privilege. Why do you have to work to survive? Live your life. That's your birthright. That can only happen, actually, when production is not necessarily done by human. And it's not far anymore. So the future of life can be great, right? We're all going to lose our jobs. Some maybe sooner than others, right? But we are going to have a lot of income, cheap or free energy, travel anywhere where you like. We probably would exhaust the Earth, cities, countries first. Then probably you want to try, even the spaceships are not going to be that expensive anymore. You may say, which planet I want to travel next week, right? Why not? Have fun, right? So AI is not the doomsday. AI is not going to take over the world. The harms, the troubles that are done to the Earth is not done by AI. It's by humans. Right? There's no such a thing as a responsible AI. Although we are launching a center called responsible AI, so we get a lot of money from that too. But no such a thing as responsible AI. It's only responsible or irresponsible human. So the key thing is about human, right? Not about AI. And there's no reason for us to be afraid of AI, right? They're going to be blessing. But the human part, we wish to improve. Okay, that's all. Thank you very much.
Do our audience have any question? Maybe just one question before the break. Okay, yeah, I have a question. So actually, I also read the book of why. Yes, I also want to try to using some causality into the computer vision and multimedia, but I found one main factor is the subjective, right? I read some papers. I think their causal map is not correctly incorrect, but you know the book also say it is subjective. So from my aspect, I think their causal map is wrong, but maybe they think that the causal map is correct. So how to, you know?
There's a lot of mistakes in that book. So I have that book too. So so you see they claim, Juniper claim that humans or Homo sapiens is the only species that can imagine, right? I believed him, right? Initially, I got laughed at by psychologists and also animal specialists. They say, actually, a rabbit or mice and squirrels, a lot of animals can imagine too. So there's a lot of, so I mean, you might be one expert, you might be expert in one field, doesn't make you expert on other fields, right? So there's mistakes like that in that book. So we are not the only species that can imagine. imagination is not the only reason that humans are so special and become the top of the food chain. No, it's not. You know, the key problem for you may find the book doesn't help you enough is that's a book of why, it's not work of intervention doings. It's only about why, and it's not a completely answer for the why neither. Because and most of the causal AI groups, they are from the old classic school, so they work on the smaller problems. They have to prove the uniqueness of the recovery. They often abandon whether that's the correct recovery. They only see whether that's unique. So and often they impose a lot of functional space restriction. It's like you have a huge forest, right? Different nice trees. They hang themselves on one tree and lost the entire forest. That's why it's not working. Right? But if you keep the forest, it's going to work better. If you so you can embrace with large language models. Right. Otherwise, if you try to bypass or avoid large language models, or if you avoid the current powerhouse of AI and only do the narrow sense of causal AI, it's like a floating paper airplane. The airplane can be very light, pretty, you can do nice drawings, and you can fly. Paper airplane can fly, but it's not the same as the big metal airplane. Which one do you really want to build? I want to build the ones take people to fly, right? Not just to exhibit your paper floating skills.
Maybe we should focus on a specific problem first, and then try to, explore.
Not necessarily, but it's better to have both. You need to both. You have to have a hands-on experience. You know what are the problems, real problems. So you get connected with the world. You're not cut off from the world. But you also need to have a holistic view of not only now, but the future. So you need to see far as well. Otherwise, your life can be focusing on the little details every day. The life can be very miserable. And you would not have enough drives for yourself. You can do that for a few years, but one day you'll be exhausted.
Yeah, sure. So, Professor, you believe in causal optimization. Maybe some people also say they want to have SGD optimization of their life. Maybe just a random go around and then SGD.
Causal can use SGD too. They are not contradicting to each other. Causality is essentially the way of change. Are we not always in the state of change? So unless you deny change, are we living in a frozen world? No, it's not a dead, frozen world. It's changing. It's alive. So don't deny it. Causal AI is only asking you, don't deny you're living in a changing world. Accept it as a blessing so you can be better prepared. You can fulfill your dream better.
SGD plus the causal.
Maybe not just SGD, right? There could be other ways.
Sure. Maybe Adam or right. Yeah. Oh, thanks. Thanks, Professor. So that's all for today's talk. And later we will have a break. And after break, we will have the challenge winner to present their work. Yeah. So maybe we have 10 minutes to have a break. Yeah. Thanks.
Yeah, I think now I think that that's very good for the 3D reproduction. So you need virtual reality device. The partner is still not so great. Yeah. People can do it for half an hour or so, and then they get tired. Yes. That's the biggest problem partner is. Yeah. So we need to shift our focus from accuracy to efficiency, right? So well, I mean, unless the hardware gets better, it will not really feel. Right now, it's just a small. Most people don't have 3D glasses. Yeah. They're still expensive. So how much do you do? The regular video stream well. Yes. Also, there's some challenges with all the meeting. It's people it's our but if you just do regular video streaming, it's difficult to make it better. It's already works. Everybody's using YouTube. Yeah, you need to just follow some techniques to solve our computer. Yeah, you need to find a special use case. Otherwise, the regular use case already works. So if you want to do, let's say, video streaming on low resource devices, maybe there's something more interesting there. People have it's difficult to make it better. You can maybe 1 or 2% or so. It would be difficult to get out into so we're interested in that and coming with the multimedia systems conference. That's usually with techniques.
你是乐老师的，你是刘倩。
Yes, we get well, people TMM very tall. This paper there's no single journal. 我是杨老师写的。
杨毅老师的学生。
对。
你叫什么名字？
我说这个。
啊，对。我把这个这个。
This is a bunch of just doesn't work. There's no show. Look at the website and I looked at that. There's no program.我有学微信的 application 的 information， 然后the first shot from the tutor was pretty interesting to see what's already worked on. And yeah, no, I mean the topics are good. It's just the information doesn't seem to be regularly. I think Here. Oh yeah, that's okay. All right.
And you have to know that it's
That's okay. Yeah. Okay.
Okay.
Okay, good. Thanks.
The camera, open the audio. Okay, I see this. Good now.
So I have to see.
You
How
use
can-
this to collect.
Okay.
This to go through
Yeah,
and
perfect.
then for the.
Perfect. Thank you.
Thank you.
So thank you, and thank you for attending to my talk about our solution. We called it Optimizing Geolocalization with K-means re-ranking in challenging weather conditions. Here we have some pictures of the data set. I just want to dive into some details about it. We have this drone images that are taken around some buildings, and our goal here was to match the drone images to satellite images to locate where the drones actually are. And in this year's challenge, we have some new conditions. Basically, we nowadays focus on weather. Like normally when you're flying with your drone, it can appear that you have something like fog, rain, snow, or some combinations, of course, which is pretty hard. As you can see in some of the cases, the combination of fog and snow is pretty heavy to see what kind of building it is. And also some other conditions like night are simulated, or overexposure, like in a very bright day. And wind, of course, is also a kind of problem for drones as they are flying up above. And first, I want to dive into what our first work was in this domain for cross-view geolocalization. We treated this as a retrieval problem, and we reused our pipeline from the ICCV paper Sample for Geo. We used therefore two convnects with shared weights. And normally for the street view, cross-view geolocalization, we have like the satellite images and street views, which we're trying to match with the info and CELOS. The advantage of this pairwise loss, we have the positive images, which act as the positive pair, and all the other images in the batch are like the negative pairs that are contrasted against it. So also we introduced there some kind of similarity matching sampling. So we find hard negatives to sample them into the batch. So for this iteration of the workshop, we, as I already mentioned, adapted the architecture. We still have some image encoder with shared weights and also the info and sealers. But this time we switched from the ConfNext to the vision transformer with Dino V2 weights. I will literally explain why. And of course, for better domain adaptation, we used some synthetic weather augmentations for higher generalization, as well as different dropout techniques to mask explicit parts of the buildings, so we can focus more on the overall scene. So here is the results for the part 1. I will dive into the re-ranking later. And as we can see, the baseline from the workshop paper drops really hard in the recorded one. This is because, of course, it's not trained on the newly data. When we trained our ConfNext from the sample for geo approach, it's okay, like nearly 60% of recall at 1, which is pretty nice. And as soon as we add the weather augmentations, we can see a pretty good rise in performance. But it's still not there where we were at the end of the competition, of course. What was pretty interesting, when we switched simply the model to the vision transformer, especially the Dino V2, we have some pretty nice performance improvements without any additional training. And it's interesting to note that the vision transformer base has the same amount of parameters like the ConfNext. So this kind of initialization for the vision transformer performs really, really good. And as also we can see, of course, as soon as the parameter count rises, the performance improves as well. So for the second part of our paper and workshop submission, we focused on a cluster-based re-ranking. Most of the re-ranking approaches have this problem. You're having to calculate the similarity matrix multiple times and have to re-rank them. And this is quite performance expensive. Therefore, we applied k-means clustering as a kind of pseudo classification for the query images. So we just did this for the query images, not the gallery images, which is more performant. And then we used the similarity, the average similarity we calculated from these cluster centers to add them to the actually queries. And this helped to push the query images more near to the gallery images that are matched. And here again, we can see for the results even with large transformers like the Dino V2 Giant still improve when using re-ranking. So yeah, that's quite nice. And I think it's also secured the first place in this kind of competition. So for the discussion of our work, the parameter size of the transformer, I mean, it's logical, the bigger the better, the more parameter, the more degrees of freedom we have. But it's kind of a slow inference, of course. This is something we should discuss in further work. How can we achieve the same kind of performance with much slower and much smaller models? Also, something about our re-ranking. While the re-ranking works nice, it still introduces a new kind of hyperparameter that you have to tune. So a suboptimal choice of the number of clusters can also degrade the performance. And now to my conclusion about this work. What we saw in this kind of challenge, the pre-training matters very much. As I said before, it was astonishing how the vision transformer performed better. And then even when we compare different initializations for the vision transformer, like clip-based training or Dino version 1 versus version 2, we found that the Dino version 2 performs very, very well. Also, of course, in-domain augmentations are invaluable, and the bigger the transformer, the better. And on the right, we can see just some TSNE plot where we showed, okay, even when we don't train on any classification task, the info NCE loss aligns the query feature and the gallery feature pretty nice in some kind of distinct classes. So that was my talk. Thank you very much.
Thank you. Maybe one quick question. Have you ever tried the model example? For example, we train multiple base transformer and Dino V2 base and maybe
assemble it or
sorry?
And then ensemble it or
just plus them score and aggregate the ranking score and re-rank.
No, we don't. We didn't. I mean, it was very short. We were very short on time actually, but
sure.
this would be very interesting.
Have you ever tried, adding the giant, large base, their score, maybe using a weighted sum and to fuse them together?
No, we didn't.
Maybe it can be
A little bit, I think, as well.
Sure.
So, thank you.
Yeah, so next we will have the two remote speakers, and they do not come, so they have provide us the videos, and I will play the videos. Okay, the second winner is from the University of Science and Technology of China, and it is from the Professor Zha's team. Right. So I will play the video. I will stop sharing and play the video. Okay. Sure. Sure the store. Right. Okay. So their video is within the downloads.
Good morning, everyone. My name is Qinfeng, and I am from the University of Science and Technology of China today. I am here to present our challenge report on an effective method for geo-localization in adverse weather conditions, which we call MGAW. This study aims to address the challenge of matching drone view images with satellite view images, especially in complex and varied environmental conditions. My presentation is divided into 4 parts. Visual geo-localization is a crucial task that involves determining the geographical location of an image by matching it with another image from a different perspective. This technique has broad applications in drone navigation, aerial positioning, and 3D modeling of urban architecture. Typically, this process involves using images captured by drones at different altitudes as queries to locate the most similar satellite images. We can extract geographic data from drone views and accurately determine their coordinates in satellite images. This capability facilitates further exploratory work in related fields. So this task is generally considered an image retrieval problem. The key is to design a series of deep neural networks to learn discriminative image descriptors. However, traditional deep learning-based methods often fail under adverse weather conditions such as rain and fog due to insufficient adaptation to the domain shift between training scenarios and diverse test environments. This limitation is particularly significant in real-world applications where drones operate at low altitudes and face various environmental interferences. To address this issue, we propose a data-driven approach using a general model to enhance the method for geo-localization. In adverse weather, our framework employs EVA-02 for feature extraction, a vision transformer model enhanced through stable optimization techniques. EVA-02 benefits from masked image modeling pre-training, leveraging robust clip visual encoders. This enables EVA-02 to extract pivotal information from drone and satellite images, even in the presence of environmental disturbances. Our method consists of 2 main components, similar to a Siamese network. As illustrated in this figure, these components handle drone view images and satellite view images, respectively. Then we use the EVA-O to model as the backbone network. EVA-O2 is an improved vision transformer that extracts the most valuable features through large-scale pre-training and knowledge distillation. The pre-training strategy involves feature-level knowledge distillation, where EVA, a standard bit encoder acting as the student model, mimics the structure and visual encoder of the larger vision transformer models. The prediction targets are generated by the teacher model clip, which provide image text aligned visual features. Given the nature of our task, which involves one-to-one matching between drone view and satellite view images, we face a challenge with the University 1652 dataset. In this dataset, each location is represented by multiple drone view images, but only a single satellite view image. In our task, Q represents the encoded drone view image, referred to as the query, while R denotes a set of encoded satellite images, referred to as the references. In each set, there is only one positive reference, R+, that matches the query Q. The inference loss function utilizes the dot product to compute the similarity between the query image and the reference images. The loss is lower when the query image is similar to its positive match and higher when the query image is dissimilar to the negative references. Ri, this loss function measures cross entropy as the similarity between views, promoting higher similarity for the positive pair and lower similarity for the negative pairs. Traditionally, inference loss has been employed asymmetrically in unsupervised representation learning for images, where one positive example is contrasted against -1 negative examples, n being the batch size. This allows for effective contrastive learning across numerous examples within a single batch. Given the University 1652 dataset as structure, where multiple drone view images correspond to a single satellite view image, a customized sampler is required to prevent the presence of multiple positive examples for the same ground truth label within a batch. This ensures that each query is uniquely paired with its correct reference, thereby maintaining the integrity of the learning process. To simulate different weather conditions and visual effects, we employed a variety of augmentation techniques, including snow, rain, fog, and motion blur. Additionally, we used the multiply augmenter to simulate darkness and overexposure. We combined these augmentations using sequentials, such as fog combined with rain, fog combined with snow, and rain combined with snow. By integrating these diverse augmentations, we aim to create a dataset that better reflects real-world conditions, thereby improving the generalization capabilities of our model in adverse weather scenarios. In our experiment, we resized each input image to a fixed size of 448 times 448 pixels and applied various image augmentation, such as random crop, random perspective, random affine, and random horizontal flip. During training, we used HGD as the optimizer with a momentum of 0.9 and weight decay of 5 times 10⁴. With a mini batch size of 12, the initial learning rate was set to 0.01 for the backbone layer and 0.1 for the classification layer. As a backbone network, EVA-O2 was selected for its superior performance on visual tasks, especially for feature extraction in complex environments. The IVA-0 model demonstrates excellent robustness in bad weather conditions and can effectively cope with light changes and occlusion problems, significantly improving positioning accuracy. The advanced features of IVA-02 are incorporated into our models through the knowledge distillation method, achieving further performance improvements and ensuring stable performance in all weather conditions. To evaluate the improvements brought by different feature extractors, we tested variants of our method with different backbones. Specifically, Model 1 and Model 2 denote the model with Connext V2 as the backbone, while Model 3 and Model 4 denote the model with IVA-02. We analyzed that one of the key advantages of the Vision Transformer framework, particularly IVA-02, is its ability to focus comprehensively on low-quality and low-frequency features, unlike convolutional neural networks, which tend to emphasize high-frequency features such as edges and textures. Transformers are designed to capture global context and long-range dependencies. This makes them particularly effective in handling images with varying lighting conditions and other environmental disturbances. IVA-02, with its advanced attention mechanisms, can better extract and utilize these low-frequency features, leading to more robust and accurate geo-localization in adverse weather conditions. In this study, we proposed an effective method for geo-localization in adverse weather conditions, MGAW, by combining advanced transformer architectures such as IVA-02 and extensive environmental condition simulations. Our method significantly improves the performance of cross-view geo-localization systems in complex and varied environments. This work paves the way for developing more reliable and accurate geo-localization solutions, suitable for dynamic and challenging real-world scenarios. To further enhance the practicality and robustness of our method, we plan to extend the MGAW approach to real-world applications such as urban surveillance, disaster response, and agriculture. Additionally, we will explore the integration of our method with other sensor data, such as GPS, LIDAR, and IMU, to improve the accuracy and reliability of geo-localization. We also aim to investigate the geo-localization capabilities with other views, including ground level and street view images, to broaden the applicability of our method. Finally, we will explore whether more efficient application can be achieved by upgrading the image dimension to the video field, enabling real-time positioning capabilities similar to those seen in science fiction movies.
Okay, good. So this is the video from our second winner, and we will have the last video from the third prize winner. Sorry, I just put him here. So this is our champion, and this is the previous second place winner from Professor Zha's team. And the second winner is by the team of my colleague from University of Macau, and they also provide a video because they cannot come here, and
Hello everyone, very honored and very lucky to share our paper title is WAGL, Extreme Weather Adaptive Method for Robust and Generalizable UAV-based cross-view geolocalization. And this is Sun Jian speaking. I'm a PhD student from the University of Macau. I will introduce our work from the following four aspects. First is the background introduction. We take part in the UAVM Challenge 2024, and this year the challenge introduced a new cross-view geolocalization dataset and different weather, which is called University 160,000 WX. The following is representative images from this dataset. We can see that, for instance, rain, snow, fog, or the combinations can cause significant interference with the content of the images. The right side shows the LP method after extending the gallery site of university dataset and introducing weather disturbances. You can observe a sharp decline in the average precision, indicating that this issue urgently needs to be addressed. We can see that the addition of extreme weather factor not only results in significant domain differences from the original joy images, but also creates larger gaps between the joy and the satellite images. Therefore, how to obtain robust features has become a key issue that needs to be addressed. This is the overview of our network structure. First, we utilize the cross-domain sampling strategy to obtain P times K images, where P represents the number of different identities and K represents the number of samples per identity. A VLT-based image encoder was employed to extract features from draw and satellite images with the GEM pooling serving as a feature agitation module. And the training was supervised using cross-weather triplet loss and eddy loss. The key observation of our work is that self-supervised or unsupervised pattern are both critical for strong cross-view geolocalization performance. In our approach, we employ the following strategies. First, we emphasize exploring and using powerful CMS self-supervised backbone and unsupervised agitators to achieve domain adaptation. From the data perspective, we simulate various weather conditions and use the data augmentation methods to narrow the style differences between training and testing drawn data. And we also introduce a new cross-weather triplet loss, which minimizes the domain differences between joy and satellite imaging and the different extreme weather conditions. First is the feature extraction process. It's the most critical step for cross-view geolocalization. The classical approach is to use a seamless network architecture, which means the two different feature extraction branches share weights. The advantage is to better map the shared different platform features of different views into a higher dimensional feature space. Inspired by the universal visual localization algorithm unlock, we used Innovative as the large-scale trained backbone in this challenge to enhance the model's generalization performance and different weather conditions. Specifically, we used seamless network structure, and in the training process, we found the model with only last two VLT blocks trainable, while the rest of the other layers were frozen. Next is the feature agitation part. We employ unsupervised generalized mean pooling as our feature agitation module. Compared with supervised trainable modules, our unsupervised approach offers superior generalization capabilities, making it more adaptable for the generalization and multi-weather conditions. From the data perspective, we use multiple simulated weather data augmentations, specifically using the image org data augmentation library to randomly apply various weather conditions such as fog, rain, and snow. And the formula for this augmentation method can be expressed as follows, where I represents the input image, H and W denotes the image has, and Y M stands for the randomly generated mask for snow, rain, or fog, and W represents the brightness values for snow or rain or the density of the fog. Furthermore, we propose cross-weather triplet loss As the CVGL can be framed as a metric learning problem, the objective is to map images from different platforms into shared space. In this space, embeddings of the same geographical location should be close to each other, while the embeddings from different locations should be as far as possible. And the image left refers to the triplet loss, where A is an anxious symbol, P is a positive symbol, and N is a corresponding negative symbol, with margin being a threshold parameter. And in the right, B describes our proposed cross-weather triplet loss that we introduce simples and different weather conditions and calculate the cross-domain simple distance DAP and DAN between joy and satellite simples. The new loss function is designed to work as synergistically with different weather conditions and image views. The specific calculation formula is as follows. Additionally, regularization term of absolute distance DAP mean between positive symbol pairs was introduced to further reduce the absolute distance between these pairs. Next is the experiments part. We compared with the sort methods such as RPN, TSM, and CCG, and we also adopt the ensemble method, including transform-based DNV2 and CM-based common-based networks. The experimental results indicated that ensembling networks with different architectures can achieve significant improvements. Specifically, we use an averaging based soft voting method to ensemble these different models. And here are some experiment results of an evaluation study, such as different agitation measures, different image sizes, different backbones, and different combinations of the loss functions. And here we show the GradCam++ visualization of drawing images under different weather conditions. And the right side visualizes the trial results, demonstrating that our method achieves excellent retrieval performance even under extreme weather conditions. Okay, here is a quick summary of our work. First, we emphasize exploring self-supervised pre-trained backbone and supervised agitators to achieve domain adaptation. Additionally, from a data perspective, we simulate various weather conditions to bridge the gap between training and testing drawn data through the data augmentation method. And also, by employing cross-weather triplet loss, the domain gap is further minimized, and our work can effectively learn and adapt to these various weather scenarios. Okay, that's all. Thanks for listening.
Okay, good. So this is all for our today's workshop, and thanks a lot for our organizing team. Actually, I'm getting very fat from Singapore, so this is my previous selfie. So yes, our team is me, Yu Jiao at Shanghai Tech, Tingyu at Hangzhou Dianzi University, Chen Chen from the UCF, Zhu Penfei from the Tianjin University, and Richard Hartler. He has another meeting, so he did not come here. He is from the ANU. So thanks. And I will, if everything goes well, I will upload our video to the YouTube and Bilibili in China version YouTube, and hopefully more people can see our video online and check it later. So thanks all. Yeah, this is the end of our workshop. Thank you. Okay, stop sharing.